We're welcoming Ralph Keeling tonight, who's in charge of the Keeling Curve at the Scripps Institute. And he's got 2 lab sites on carbon dioxide and measuring oxygen in the atmosphere. He went to Yale and Harvard, and his father was the originator of the Keeling Curve, Dr. Keeling, and so he is another Dr. Keeling working on the same project. So I'd like to welcome Dr. Ralph Keeling to our group and take it away.
Okay, thanks, Joy. I'm happy to be here. Of course, I'm a scientist, and you're part of a climate action team. And I assume you have ideas of what you want to do already to some extent. And so, what am I doing for you? What I thought I would do is just go through some of the stories about carbon dioxide and climate that come from my father and me. And part of that is reinforcing that in some ways, the climate problem and the science of climate change really did start right here in San Diego. So it's kind of an origin story. And it also will give you a perspective on the global situation as I see it. I'm not going to come away with recommendations of what you should do. So one of my
Understood.
One of my the challenges I faced in giving talks like this is that of course I'm presenting science, and it's not very happy science. And of course, people want to feel some kind of empowerment and purpose coming out of it. That's not really what I do. So as much as I like to think that there are people like you doing things, I'm not here to give a pep talk. I'm here to answer your questions about the big picture. All right. So that's what I hope. I'm serving some role. I mean, I do have ideas of what one might do, but it's not something I've really invested in to the extent of others around that you might be referring, might getting guidance from. So I assume you can see my first slide. Is that correct?
It looks good.
Yeah. Okay. So this is about rising CO2 and other stories. So what do I do? Among other things, I simply measure how much carbon dioxide is in the atmosphere in different places and over time. Here's a picture of me on an airborne campaign where we're flying around taking samples and measuring the air around the world, not just carbon dioxide, but lots of other things at the same time. And I also measure more than just carbon dioxide. I'll say a little bit about that. But we spend a lot of time trying to figure out how to get good numbers. So measuring something is not just sticking a probe out there and reading what it says. It involves lots of care into figuring out what might be going wrong and whether you got a good sample and whether your instrument is calibrated and whether it's calibrated the same now as it was 20 years ago. So there's that kind of effort that goes into it. And it's not just me, it's a team of people. And the community of doing these kind of measurements isn't just my group at Scripps. There's an international community doing these kinds of things. I ended up after an early career thinking I might go in other directions, actually following in my father's footsteps. So he was the person who pioneered modern measurements of carbon dioxide. He's responsible for showing that carbon dioxide was in fact building up in the atmosphere. And that was the work that put the problem of climate change squarely on the research agenda and and eventually on the policy agenda. So he played a really critical role. So what did he do? He got his PhD in the mid 1950s from Northwestern University in polymer chemistry. The future was plastics. and he was studying polymers. He didn't like the idea. He grew up in Illinois. He didn't like the idea of going to New Jersey and working for the likes of DuPont. He had been exposed to the mountains of the West as a child and a young man, and he saw his future somewhere in the West, somewhere outdoors. And so he got an interest also in various aspects of geology and earth science. And instead of moving to New Jersey after his PhD, he went to Caltech to do something, he wasn't sure what, involving the outdoors and the science of the earth. He was given a project to work on carbon dioxide in rivers. No one had studied carbon dioxide in rivers before. It was the age of the endless frontier of science. And all these topics hadn't been looked at. They were pioneering. And so someone said, hey, I wonder if you can figure out what controls carbon dioxide in river water. So he went up to Big Sur, where there was a river nearby. Not too many rivers that run year round in Southern California, but he liked the idea of camping. So he was taking river water samples, but he realized pretty quickly that to understand carbon dioxide in rivers, you had to know what was in the air above the river. So he also worked on making measurements of carbon dioxide in the air. And he raised the bar for making measurements in air for no other reason than he was having fun and he was being playful. There was a new way to do it, to do the measurement that he was aware of, made possible because a new resource was this material called liquid nitrogen, which is a very cold liquid. Many of you have seen it used by hospitals for preserving samples. It's very common in labs. And it's cold enough to freeze carbon dioxide out of air. So he developed a method that was very accurate for measuring carbon dioxide in air that involved simply freezing the carbon dioxide out and measuring how much CO2 was left over and then how much air you started with. You got a measure of the fraction or the number of ppm. And he used that method to study air at various places. And he discovered, to his surprise, that the carbon dioxide level in the atmosphere was actually quite constant as long as you got to a remote place that is far away from a forest or far away from a city. This was not known. And he realized it was important because prior to this, there was already a question of whether carbon dioxide might be building up in the atmosphere from fossil fuel burning, and whether that might change climate. None of it was proven very well, but it was being discussed. And he realized, oh, I'll bet we could measure how much CO2 is going up year by year if we simply went to a place that was remote enough and we tracked the concentration year by year over time. The method, as I said, involved liquid nitrogen. Here's a picture of him applying that method. He's pouring liquid nitrogen into a little cup on a glass system. It looks, maybe many remember, I grew up in the 1960s. A television show we watched was called Felix the Cat. And there was a guy named Poindexter who was always pouring chemicals and things would blow up in the end. And it was a lab with lots of glass in it. So when I was a little kid, I walked into my father's lab and it had things bubbling and glassware and everywhere. And so it felt like exactly the kind of science that was current at the time. Anyway, here's him with this apparatus for freezing CO2 out of air. He set up an instrument to measure carbon dioxide at the Mauna Loa Observatory in Hawaii. This observatory had just opened a few years earlier, and they were looking for things to do at it. And this was a team effort. The Weather Bureau ran the station, and there was a person at the Weather Bureau named Harry Wexler who supported this work. He also had, by this time, moved to the Scripps Institution of Oceanography here in San Diego, where he had a lab and equipment, all under the director of the time, Roger Revelle, who had a keen interest in carbon dioxide, and it also played roles in understanding what might be happening with CO2. So as I said, he had shown that carbon dioxide was pretty constant if he looked in different places. So what he expected to see was pretty much a constant level at Mauna Loa that might creep up year by year. And the first thing that happened when he turned, so we actually, I should say that the measurements he did at Mauna Loa were not as tedious as this liquid nitrogen method. He also bought a commercial analyzer that he calibrated with his manometric CO2 method. So he used this manometer, this liquid nitrogen method, to measure CO2 abundance in compressed air tanks. And then he would use that to calibrate an instrument. So he worked out a kind of elaborate scheme for doing this, but it allowed him to measure around the clock at a place like Mauna Loa. And the first thing that came back was pretty much a level that didn't fluctuate. Just you see these numbers 316 up to 319, but scattering around a pretty tight range. So he said, okay, great, this is working. We're getting a constant number. As often happens when you're starting something out, things go wrong. And what went wrong was there was a power outage at the station. The generator failed. And a month or so without any data. Finally, they were able to turn it back on. And at this point, he got a lower reading, but unfortunately it was no longer constant. Now the instrument was drifting down. And so he thought something was wrong with his setup. He didn't know what to fix, but he thought something was wrong. Another power outage, and it comes back on after a hiatus. Now it started even lower and was now drifting upwards. So this was pretty discouraging. He thought he was going to get some kind of constant level, but the CO2 levels were wandering around in a way that he didn't understand. It was as though something was out of whack in his instrument. Eventually, there was another outage, but things mostly were starting to work better. But about this time, he could look at the course of what he had measured so far and realize, oh, it's following a regular pattern with season. So he had discovered that the Earth was naturally breathing in and out carbon dioxide with the season. So that's one of the first things he discovered, beyond that the levels were relatively constant. And of course, after a year or so, he could already see that the levels were creeping up. Now, we continue these measurements to this day at Mauna Loa. And here's some data from earlier this year. And this is daily values. And one of the things that we have had to face recently, well, let's see, what's my narrative here? Okay, so let's just zoom out. Here's what happens if you just look over a course of about a month. If you zoom out, you can see this up and down with the season. If you zoom out further, you can see that it's regular from year to year and going up year by year. So this is the record he put together. And now extended over time, this is what it looks like. You know, massive increase over time. This regular seasonal cycle that he saw looks pretty small in hindsight compared to what we've done to the atmosphere. So this record shows a natural breathing. It also shows human activities releasing CO2 into the air, overwhelming that cycle by causing a buildup, going all the way from about 315 when he started up to over 420 now, actually pushing 425 ppm. In the 1980s, people figured out how to extract air samples from Antarctic ice cores. So you could drill down in the Antarctic ice sheet, get old air out, and you could measure how much CO2 was down in the ice. And that allowed people to extend the record further back in time. So that's what it looks like if you go back to about 1700. You can see that when he started measuring in 1958, CO2 had already risen above a natural baseline of around 280 or 275. You can zoom further out. You can go back all the way to 0 AD or 0 Common Era. You can see that it really did rise from a fairly constant level. This is very clear indication that there's nothing natural about this. This is human activity. You didn't see anything else, you would say that's pretty obvious. Now you can go back 10,000 years. It's also clear, it's zipping up in recent years, but it didn't fluctuate by more than about 10 parts per million over 10,000 years prior to that. So there really was a stable baseline. This period of the last 10,000 years is known as the Holocene. It's an interglacial period when we were not in a deep ice age. But you can also look further back in ice that goes back almost 1 million years and see how CO2 fluctuated up and down with the course of the ice ages. and current levels are shooting way above any level that we had in the past. You can also extend even further back by, not by data and ice cores, but by other proxies that are called for establishing CO2 levels in the atmosphere in the past. And you can see that the levels we have now, over 400 parts per million, probably did exist in the past if you go back tens of millions of years. Maybe 3 million years ago, there were levels as high as today, but not for sure because the data isn't precise enough. But if you go back maybe 20, 30 million years in the past, you had levels that were as high as today. So these levels are not unprecedented, but of course the world back then was totally different. It was a world with forests on the Arctic Ocean, sea level, many, many meters higher. The distribution of forests was different because of different climate. So it was a very different world. Now, from the very beginning, there was never really a question of why carbon dioxide was rising. And that was because you could do the math and calculate how much CO2 was being released into the atmosphere every year from fossil fuel burning. There were and have been decent records of total global emissions from fossil fuel. We know the number of tons reasonably well. Fossil fuels are a valuable commodity. They're tracked in markets. And although there might be some errors, they're at the level of 10% or so. They're not the level of 50% or 100%. So we know how much CO2 is going into the atmosphere. We know how big the atmosphere is. So it's pretty simple to calculate how much carbon dioxide would go up year to year if it all stayed there, if all the extra CO2 stayed in the atmosphere. And the rise that my father measured was only about half of what you'd expect if all the CO2 stayed in the atmosphere. So the question wasn't, why is it rising? The question was, where's the other CO2 going that's not staying in the air? And there are really two main possibilities. It could be going to the ocean, or it could be going to the land. The ocean takes up carbon dioxide because CO2 dissolves in seawater, and it reacts with other ions that are in seawater, like carbonate ion. That's the CO2 3 minus thing there, CO3 2 minus. So the oceans have a capacity for absorbing CO2 because CO2 is basically an acid and seawater is basically alkaline. And so there's a kind of acid-base neutralization reaction that goes on. It's written here in the blue background. That's a reaction that buffers the CO2 rise. So the oceans have a big capacity for taking up CO2, and the oceans are a big reservoir. However, the oceans mix rather slowly. So most of the deep ocean isn't really in contact with the atmosphere at all. So it's only the top hundreds of meters of the ocean, maybe up to 500 meters, that have really played a role in this process. Anyway, the oceans have a capacity. And of course, land plants have the capacity to take up CO2 by photosynthesis. And so what I'm showing here is a kind of a schematic budget. This is basically, you know, the change in your balance is the credits minus the deficits. So the credits here are the things that are adding CO2 to the atmosphere. We have fossil fuel burning. Can you see my cursor or not? Do you see a cursor? You do. Okay, that's it.
Yes.
Okay, so fossil fuel burning. So this is the atmospheric growth rate. This is the year-on-year change in CO2. This is how much CO2 we're dumping into the atmosphere from fossil fuel burning. By the way, we're also adding CO2 to the atmosphere in lesser amounts, but still significant amounts by interventions on land, like clearing land for agriculture, where you had a forest before and you turn it into a pasture. The carbon in the trees ends up in the air mostly, and so that's an additional contribution to the atmosphere. So these are what's adding CO2 to the atmosphere, and then what's taking it out is it can be going into the ocean, and it also can be going into land ecosystems that are not being perturbed because they have the potential to absorb CO2 through photosynthesis. So this is the basic budget, and work by myself and my father went into trying to understand these other terms, because after all, he was measuring the buildup fossil fuel was known. So the difference over here was known, but the breakdown between the ocean and the land and land use has taken decades to work out, but we do have a pretty good handle on it. And the bottom line is that basically the ocean and the land are taking about equal amount. So they basically about fossil fuel, let's see, the growth rate's about half. Okay, let me go back to the slide. You can see that the buildup is about half. And of that half that's not in the air, about 50% of that's going into the ocean, the other 50% is going into the land. And the land use is adding about 10% of the fossil fuel buildup. So that's the basic story. So the fossil fuel is the main thing making CO2 rise. But we have, fortunately, an ocean and a land ecosystem that have been absorbing CO2, reducing the problem in the atmosphere. So this is just showing sort of schematically what we're doing is we're taking CO2 out of the ground in places like this, and some of it's ending up now in places like this. This would be an Amazon rainforest. So how do we know the difference? How do we know the partitioning between the ocean and land sink? I didn't add a slide that really showed this, but my own contribution to this, let me go back to this. My own contribution to this has been to measure a corresponding change in atmospheric oxygen. So oxygen levels are also decreasing in the air. It was something my father never got around to measuring, and it was a challenging measurement. And I worked out when I was in graduate school how to do that. And oxygen helps us because oxygen is going down because when you burn fossil fuels, oxygen decreases because the oxygen is taken up to burn the fuel. And when we have land use, that also takes in oxygen because you're decomposing organic matter on land. That's a sink for oxygen because it's a combustion process or a decomposition process. If the land is taking up carbon by photosynthesis, that's a source of oxygen. So you'd say, okay, what are you going to gain from oxygen you didn't already see from CO2? The answer is in the ocean, because this ocean reaction doesn't have any oxygen in it. So the oxygen behavior is different in one important respect. All these terms are pretty parallel between oxygen and CO2. When what makes CO2 go up makes oxygen go down here, and with the land, what I'm calling B for biosphere. But the ocean doesn't have that effect on oxygen. So if you measure both, you can actually do the math and calculate how much carbon dioxide is going to the ocean. And then if you know the land use, you can also figure out what's going into this residual sink on land. So the oxygen helped us work out this partitioning. And I think one of the surprises that took a while to sink in was that indeed the land is taking up carbon. The land is actually even despite human interactions on land, clearing land for agriculture overall, over the whole planet, the land biosphere is gaining biomass. So forests are gaining mass. It's kind of surprising, but it's clearly evident from the atmosphere. And there are people looking at forests who think they can see this increase. But it's still a little bit mysterious as to how this is happening. It's not too surprising that it's happening because plants do grow faster, all else being equal, if you give them more carbon dioxide, and that will cause them to gain biomass over time. But I should say it's still a bit surprising to the extent to which this is happening. Anyway, this is showing records of oxygen decreasing over time and the expected trend from fossil fuel burning, and oxygen's going down a little less rapidly. That requires that the land is actually taking up some CO2, producing oxygen. So let's put some numbers on this. So the atmosphere pre-industrially had about 280 parts per million of CO2 in it. And you can multiply that by the mass of the atmosphere and the molecular weight, and so forth, and figure out that the atmosphere had about 600 billion tons of carbon as CO2 in it. So it's only 280 parts per million, but you multiply by the whole world, you end up with hundreds of billions of tons of carbon. And I've shown that with a symbol here that is an indication of an amount. Now here's about the amount of carbon we have in fossil fuels. 1,500. So if we burn all our fossil fuels, we can, and it's all stayed in the air, we can more than double the amount of CO2 in the atmosphere. Really almost, well, 2.5 by these numbers. And by the way, the amount of carbons in fossil fuels depends a lot on what you think is economically viable. And so if you take a conservative or an estimate that counts unconventional fuels that are out there, you might end up with many, many times more than that. So the potential of humans to eventually exploit fuel is the amount we could exploit is very high compared to the amount in the air. So that's one thing to keep in mind. We are not just making, in the long run, a small dent in the atmosphere. We are massively changing the amount of CO2 in the atmosphere. So where could that carbon go? Let's look at the other reservoir sizes. Here's the oceans. The oceans have about 40,000 of these units. So they're a much bigger reservoir. However, the oceans do not have a capacity to absorb CO2 that's commensurate with the amount of carbon. To absorb CO2, you have to react the CO2 with carbonate, which is one of the species of carbon in the oceans. And that has about 4,000 units. So a better measure of ocean capacity is to look at this number here. It's still big, but it's not as big as you would expect from this 40,000 number. So as we add CO2 to the ocean, we're using this carbonate up. And when the carbonate gets low, then the ocean can't really absorb carbon anymore. Let's look at what's in plants and soils. There's about 600 units in living plants. That includes trees and their roots and grasses and so forth. That's comparable to what's in the air. So one thing you can see from that is the proposals to solve this problem by growing trees, if they're going to make a big impact on the problem, have to entail massive increases in vegetation cover on land, not small changes, massive changes. If we were going to absorb all of this 1,500, we'd have to increase the amount of plant biomatter more than twofold on the planet. Now, maybe that could happen, but it's not what people are envisioning. And by the way, that itself would have enormous environmental consequences. So it's not the plants, when they absorb CO2, it's not entirely passive. They're doing it by changing what's on the ground. Now, there's considerably more carbon actually down in the soils, down to depths of a few meters. And this carbon is less actively cycled. So it's not clear there's as much capacity to increase that, although there are proposals to add amendments to agricultural soils to improve the holding of carbon there. Really, this is more a concern than a resource, that if we warm the climate, maybe some of this carbon in the soils will add to what's in the atmosphere, making our problem even worse. So this is kind of the lay of the land pre-industrially. Now, what have humans done? So far, we've burned about 450 of these units. So I'm taking a wedge out of this pie and I'm dumping it into the air. We've also, by the clearing of land for agriculture, added about 200 to the atmosphere. It hasn't all stayed there. The atmosphere only gained about 280. So where has it gone? Well, about 170 has gone into the ocean, and rather similar amount, about 220, has gone back into the land again. So you can see that the problem has been made considerably less serious by these sink processes. And there's a lot of interest in understanding them so that we can project forward and to figure out whether that's going to continue. And although the ocean behavior is reasonably securely understood, we don't understand what's going on the land that well. And I think the possibilities include that the land will continue to be gaining carbon like this, or that it might turn around and become a source. One thing you notice is that the uptake over here is rather similar to the land use emissions. as though they're offsetting each other, but it's clear they're not the same. This isn't just regrowth of what was cut down pre-industrially. There are new processes leading the carbon to build up on land. And where's it going? Well, some of it's going into boreal forests and temperate forests, and probably some of it's also going into tropical forests, although not uniformly. Like the Amazon now, the indications are that it's not gaining carbon. Now, people talk about how much we can emit before we get to certain limits, like a 2-degree warming. And as I'll explain later, there's a way of looking at the problem that relates how much warming the atmosphere undergoes to the total emissions to date, that is the cumulative emissions, which would be measured by the size of this pie. And so to get to 2 degrees C, to stay under 2 degrees C, we're only allowed to emit basically the same amount we've emitted so far. By the way, this slide's actually a few years out of date. So actually this wedge should be a little bigger and this wedge should be a little smaller. We're emitting 10 of these units a year. So in 3 years, another 30 of these will have moved over. So this number is probably now should be up closer to 500. So there's not a lot of headroom to stay under 2 degrees C. The world has warmed up, I don't know, something like 1.2 degrees C so far. You know, we will definitely have to leave something like a third of what we think are reasonable fossil fuel reserves in the ground to stay under 2 degrees C, or develop methods for scrubbing this extra CO2 out of the atmosphere. Or not letting it in, burning the fuels, but directing the CO2 below ground immediately. This is just showing the similar breakdown for oxygen. You might worry, oh, we're using up oxygen in the air, should we be worried? And this is just showing what 10 years of fossil fuel burning does to the massive reservoir of oxygen in the atmosphere. The answer is it doesn't do much. And if you look at the total resource base, the total potential for removing oxygen from the atmosphere is actually rather small. So we're going to run out of fossil fuels in any scenario long before we have an environmental problem with atmospheric oxygen loss. So it's important to track oxygen. And some people would be happier if I told them, oh, we should get worried about oxygen loss because it's the big environmental crisis that'll wake up the world. As an honest broker here, I have to say, well, we have a big problem with CO2. We do not have a big problem with oxygen. Let's talk about time scale. So we're releasing CO2 in the atmosphere, and this is looking at a projection going back 10,000 years. If we stopped all burning fossil fuels, what would happen? Well, let's go back to this slide here. We're emitting from fossil fuel and land use. If those stopped immediately, these sink processes would continue, and that's because they're driven by the extra CO2 in the atmosphere, which is still there. So the sinks continue. So if we stop burning fossil fuel, CO2 would immediately start dropping, but it wouldn't drop all the way back to a pre-industrial baseline because we got all this extra CO2 that we've dumped in the system that's ending up in the ocean and the atmosphere, and some of it stays in the air permanently. So the time scale for that is kind of centuries to 1,000 years or so. So the CO2 would come down and it would probably drop to something like half of the present level. And then out to about 1,000 years, it would continue dropping a little bit, but it would stay there. So there's a permanent, effectively permanent change in the system by what we've done so far. And that means that there's effectively a permanent warming that's built in by the emissions we have so far. So why does CO2 matter? I mean, I think you're all aware of the greenhouse effect. And I should point out that CO2 is not the only greenhouse gas. We have to worry about methane, nitrous oxides, and other industrial gases. CO2 is the elephant in the room, but these in combination add up to also being an important part of the problem, and are areas that we also have to pay attention to. Methane in particular is a pretty potent greenhouse gas, and it's emitted from landfills and from sewage treatment and from cattle and rice growing. So it's building up. And there's concern that warming will cause methane to be released in greater quantities from forests around the world, or not forests, but from wetlands around the world. So this is one to watch. Nitrous oxide is produced as a byproduct of industrial fertilizer use. And so its buildup in the atmosphere is really tied intimately to the green revolution, which is feeding the world. So this is not an easy one to solve. There's probably over fertilization going on in some places that could be cut back, but it's not like we're going to ask people to stop eating to solve the climate problem. So this is one of the harder ones to deal with. The industrial gases are one of the easier ones to deal with. This is things like CFCs, and the gases that affect ozone also have a greenhouse effect. And mostly these are not being emitted for any reason we really care about, and neither is methane. So these ought to be solved. Nitrous oxide is trickier, as I said. But so you know about the greenhouse effect. Let's talk about, but that's not the only reason CO2 matters. CO2 has direct chemical effects that have significance. Among them is that plants grow faster. And that might seem like a good thing, and it probably in many cases is. But whenever you perturb an ecosystem, there are winners and losers. And so you're mucking with the system. And so there'll be probably extinctions driven by CO2 fertilization, for example, in the future. I wouldn't doubt it. Ocean acidification, CO2 is an acid, dissolves in water. I think probably you've heard about that one. This is harmful for shells living in the ocean that need to create calcareous shells. And that's harder as the CO2 acidifies the ocean. Another one that has gotten some little bits of discussion recently is that the buildup of CO2 may have significant physiological impacts on humans. Now, I don't want to say much about it because I'm not an expert, but the story here is that in indoor settings where CO2 can get up to, say, 1,000 parts per million because you don't have good ventilation, there's evidence that there is some impairment. So high-level cognitive functions, people don't think quite as smart. We're all getting a little dumber, maybe, if we're in a high CO2 world. And there are also other physiological impacts. And I said these impacts kick in if you're in a room with up something like 1,000 parts per million. You could say, well, what's that got to do with what's building up outside? Well, the answer is that, you know, the extra CO2 in the room is going up in concert with what's outside, because that's the starting point where your breath is adding to it. So if the CO2 goes from 280 to 450 outside, it means the CO2 inside is going to go up a comparable increment, maybe from 800 to 1,000. So the outdoor CO2 levels do impact indoor levels, which may have some physiological impact on humans. So there's awareness that this is also an issue. So a few take-home points. You know, I didn't talk about scientific significance, and you guys are all motivated to work on this problem, but the significance of this problem is well established. The greenhouse effect is not controversial. The buildup is not controversial. We understand that pretty well. So there's really no debate among the scientific community about this. I'll say also that, you know, for a long time we were talking about future changes. But I mean, just look around. I mean, the changes are really manifest around us this summer more than ever before. And the way I say it is the beast is out. And if you don't notice it, you're not paying attention. So the beast is out, and we're continuing to fuel it by feeding it more CO2 from fossil fuels. And people get it. They're not sure what to do about it. But it's serious, and it's going to grow markedly. There's a lot of changes that are already baked in. If we cut emissions to zero today, I thought I was going to talk about this, and I thought I had slides about it. Let me go back to the slide here. So you might think that if we could cut emissions to zero, the problem would get better because some of the CO2 would go away. So it makes it look like the problem was front loaded, that the problem is worse in the first few decades or 50 years or so, and that goes away. That's true from the standpoint of what's happening with carbon dioxide. But there's a countervailing effect, and that is that it takes a while for the world to warm up in response to the CO2 we've already emitted. So there's a lag as well. So if you looked at how the temperature responded to this, it would not catch up immediately. So the climate has not caught up to the 420 level yet. It's still a few decades behind. It's still sort of back at the 260 level because it's lagging behind. So what happens is the CO2 dropping, the temperature is still trying to rise because it's trying to catch up to the previous level. And by the time CO2 stabilizes, the temperature kind of stabilizes at a level. So it turns out that the amount of warming you get out is really proportional not to how much CO2 is in the air because of these lags, but how much emissions you've had so far. So that's why, back on this slide here, I could look at the allowance for 2 degrees C and say, okay, it's an amount of pi on this chart, because this is the amount of CO2 we could emit. It doesn't matter that much what order we do it in, it just matters that we stay under that amount. And by the way, this perspective is what's grounding this concept of net zero. So net zero is the point that we're not adding any more CO2 to the atmosphere. Or the human interventions are adding up to zero. It's not that these other things, the natural sinks are not counted in net zero. It's just the human interventions. And that's the point that we're no longer eating away at this pie. We're squirreling some CO2 back into some other similar pie to make sure it adds up to zero. And we have to get to net zero in order to stop the problem from getting worse. So net zero is not the point where we've solved the problem. It's the point at which we stop the problem from getting worse. And we're a long way from net zero because we're emitting so much carbon every year to the atmosphere, and we're emitting other greenhouse gases. Okay, so take-home points. The changes are quasi-permanent. So that's what I was just trying to emphasize. This is all about the global picture, and the impacts on people depend on what's happening locally. But local impacts are likely to be scaled pretty much in proportion to the overall warming. So although we don't experience global warming, we experience consequences that scale with it. So for example, one way to look at this and be sort of realistic about it, if we got serious about cutting emissions, you could imagine that we might be able to ramp down fossil fuel burning as fast. Well, this is something I think is certainly doable. There's questions of how fast we can go over to renewables, but one thing that we almost certainly could do is we could ramp down fossil fuel burning as fast as we ramped it up, because that plays out over decades, and it's enough time for technology to change because we experience it. It's how we got where we are. A ramping down as fast as we ramped up means that we would burn as much on the way to zero as we emitted coming to where we are now. So we would basically double the amount of warming we've had so far. So in that sense, because we can't get off fossil fuels fast enough, there's going to be continued rise, and it's proportional to how much we burn when we finally get to net zero. Other points I didn't talk about this: sea level. Even after we stabilize temperatures, let's suppose we get to net zero and the temperature eventually stabilizes, sea level does not stabilize at that point, and that's because we have a warmer climate and the ice sheets are in equilibrium with a colder climate. So Antarctica and Greenland could probably continue to melt out for 1,000 years or more, contributing to continued sea level rise. And so it might, if the sea level rise is slow enough and plays out over centuries, it's hard to know what that would do, because that's about the time frame we build a city or rebuild it. So, but still there'll be unfortunate consequences for that. And I would say, from a scientific standpoint, we're still in surprise mode here to some extent. I don't think the scientific community adequately appreciated where we'd be at this point with regional climate changes and droughts and fires and storms. You can talk about it, you can predict it. The models give us a picture of what's happening globally. The models are not that good locally. I think we may still be in for surprises ahead that are unpleasant surprises. So and in any case, we're not through with this yet. My guess is we'll probably see another degree or see a warming before we put a break on this. And we need to try every way to do better than that. But it would be silly not to be realistic about what the chances are getting there. As for Southern California, it's not my specialty, but you can highlight things that affect us. Heat waves and droughts, obviously, fires. We're losing snowpack that impacts water supply and sea level. So these are all big impacts. At the same time, we have amazing potential for moving to renewables because we don't have big winter heating bills and because we have such amazing solar resources and some significant wind resources. So we ought to be setting the example for how to do this because we're rich enough to do it and we're smart enough to do it. And it's fun. So we should just get it done. That's my feeling. All right. And this is turning into being a little poetic. So, this is kind of a sad story of changing the environment permanently because we did something wrong. What did we do wrong? We're burning fossil fuels. We really shouldn't be burning fossil fuels. So the story, if I look for an analogous story that's been written long ago, it's the story of Adam and Eve, and the forbidden fruit is the apple, and so you eat the apple and you change the world forever. So there's no going back. The Garden of Eden is in the past, and you have to work forever to overcome your original sin. And our original sin is not eating the apple. Our original sin is burning fossil fuels. And we're going to have to pay the price for it for centuries to come. Here's a picture of my father taking an air sample. He loved to camp. This was later in life. He would go out and take samples like this. Here's a picture of me at an earlier point with my oxygen analyzer with my father there. Here's a picture of my father with that person in the background is Roger Revelle, the Scripps director, and also really luminary who really helped put the climate problem on the research agenda, using my father's data to talk it up and to make it.
I'm not seeing the pictures. Is everybody else seeing it?
Are you seeing pictures?
Yes.
Yeah. No.
Yeah, I am.
Okay. It must just be me then.
Yeah, sorry about that. So that's it. That's the whole show. But I'm happy to take questions. I probably touched on a lot of things that didn't get adequately explained, so please fire away.
Anybody with questions, will raise your hand.
Yeah, am I policing? I see a hand by Gary. So, but you might need to you might need to be the intermediary.
Mike Bullock, go ahead.
Hello. Yeah. Okay. Thank you.
Okay. Sorry.
So, Ralph, are you aware that the state of California has climate mandates? The first one's in 2030, and it's 40% below what we emitted in 1990. And the CARB scoping plan that was released in December last year tells us what we'll need to do to achieve that 2030 climate mandate. So I wonder if you are aware of those things, if you follow
generally,
the political side of this stuff.
Yeah, California's got a reasonably progressive plan. The devil will be in the details and whether we actually stick with it.
Yeah, people are ignoring it. One thing it says, we have to price car parking. It says we have to have a road use charge. And I guess everybody here is aware that our representatives are currently removing a road use charge from our regional transportation plan. It was approved by CARB, And now I doubt CARB will approve their work. They're spending $1.5 million to remove something which CARB came out in December and said we must have pricing because we must reduce driving. They've done the math and they know that we can't electrify our fleet fast enough. So we have to do both things, electrify our fleet very, very fast and reduce driving. And they've got the numbers. And then they say to do it that fast by 2030 is not very far away. And so to do that, you have to use pricing strategies, and that's parking and the road use charge. So we're completely
Mike,
failing, it seems to me.
What's your question, Mike?
Do you agree that we're generally failing? You said California is pretty progressive, but I'm just saying here in San Diego County, our SANDAG board of directors is doing just the opposite of what CARB says we must do based on the math. And that's just the climate mandate, which probably isn't enough, but it's certainly something we have no chance if we don't at least do that.
Yeah, I don't disagree with what you're saying. I haven't, you know, you probably thought harder about the nuts and bolts of this. You know, one thing I worry about a little bit is that you have to do this at a pace that's politically sustainable. And we've seen this at the national level where you just get suddenly it kicks back, everything gets rolled back, and suddenly you're a election cycle or two behind the curve because there was such backlash. So the strategy, so there is a danger, even though the climate problem is serious, there is a danger that the political process will get pushed too fast and the backlash will lead to a slower outcome than if you were smart about it. So maybe the parking mandate, the parking mandate is over the top from the standpoint of political acceptability. I'm not saying that, but one has to be cognizant that the people, you know, on SANDAG and so forth might see the landscape clearly enough and realize, oh, if we're going to get there, we're going to get there a slightly different way. So,
they don't have a way. Believe me.
I think Gary,
Yeah.
The next question, I want
yeah,
to.
anyway.
Gary had one.
Yeah, I had a question about measuring the acidity, carbonic acid in the ocean. Has that been tracked as well as the carbon in the atmosphere? And if so, how far back has that been tracked?
Yeah, well, actually, my father started measuring carbon properties of the seawater with regularity in the mid 80s or early 80s. So we have, well, let's see, no, late 80s. Yeah. So we have records going back to that time frame, and you can see the carbon building up, and you can see the pH changing as you expect.
Mm-hmm.
So there's really no surprise there, but it's important to track it and to prove we understand what's going on. Those data are relevant, for example, for understanding what might happen if you were going to try to intervene and change the chemistry of seawater to take more CO2 out of the atmosphere, something called alkalinity enhancement. People are talking about that as one of the kind of geoengineering strategies. But yeah, we do see what's happening in the seawater. It's harder to measure because there's a bigger background of carbon in the water, and it fluctuates more as the currents change and year to year. So it's not quite as the Keeling curve of the ocean is a little messier looking, but it's still compelling. I mean, I could have shown that, but yeah.
Are we very far away from being totally saturated? In other words, so it can't accept any more CO2, or how far off is that?
Really far and away, because it's a soft endpoint. It doesn't have like a titration that comes squarely to an end, because the equilibrium reactions sort of make it gradual. So it does slowly lose its efficiency. And as CO2 builds up, it loses progressively more efficiency. But the ocean still has a big capacity. I mean, there's quite a bit of headroom in that.
I imagine you have to measure it in a lot of different places in the world, where as you pick Mauna Loa in Hawaii to measure the atmosphere, but I imagine in the ocean, it's so many currents move around and everything. It would be hard to measure that. Is that correct?
Yeah, it fluctuates. There's more variability from place to yeah. So the difference is that the atmosphere is kind of mixed up quickly. The whole atmosphere, the air at the South Pole and the air at Hawaii, within if you released a contaminant in the atmosphere, you could detect it within a year at the South Pole or less, right? So the air is churning up and mixing around rather quickly. Whereas you release something in the Atlantic, it might take centuries before it got in the Pacific. So the ocean is
I
much
want to
less
ask Cynthia to
homogeneous.
ask her question.
Pardon?
Cynthia, you have a question?
Who?
I was answering
Yeah.
Gary's question. I thought they were
I'm
fair.
done.
Yeah, go ahead.
I'm okay.
Glenn had his hand up, and Cynthia has a question, and then Joe.
Yes, Dr. Keeling, you hear me okay?
Perfect.
Okay. Along the same lines, does the temperature of the ocean affect its capacity or its ability to absorb CO2?
Yes, it does. It's not a first order effect on the controls. So there's a standard line coming, a standard sort of talking point from the skeptic community that says, oh, it's the warming that's causing CO2 to go up, and it's because the oceans are getting warmer and they're causing CO2 to build up into the atmosphere. It's totally wrong. I mean, it's true that the oceans were causing the CO2 to go in and out, up and down in the ice ages. We understand that pretty well. It's not what's happening now. And you can just do the math. I mean, if you increase the temperature of seawater by 1 degree C, that would give you a 4% increase in the CO2 partial pressure in equilibrium with it. CO2 has gone up way, way more than 4%, and the ocean is sort of warmed about 1 degree C. So CO2 has gone up about 50%. That's way more than 4%. So it's relevant at that sort of 5% level.
Okay. Then one more, if you don't mind.
Sure.
Forests, when trees grow, they absorb carbon dioxide. If there's a forest fire, that carbon dioxide is re-released into the atmosphere, correct?
Exactly.
But if the trees are used to build homes or any industry where they're not burned, that carbon is locked into that, at least until a home burns or something, right?
You said it perfectly. I hope everyone was listening.
Okay. I was exposed to a company a couple of years ago that is growing giant bamboo for the building industry. And I'm not sure what their motivation was, because they're getting some carbon offset credits too from the federal government, but and maybe even some other countries' governments. But the purpose behind them was they were growing this giant bamboo that was extremely fast growing, and because it was so fast growing, it absorbed a whole lot more carbon dioxide than most plants. There certainly the uptake for plants varies between the kinds of plants, right? The amount of absorb. So I know you're not really offering solutions today per se, but how can one find out what kind of plants we should be planting to assist in that?
Yeah, well, I mean, I think it's exactly the calculation you did. It's how much biomatter, it's how much carbon is in the product that's stored or sequestered. And yeah, growing bamboo and using it for building material sounds like a positive to me. It'll be driven by the market for that kind of material, and it might not end up being that big a market, and so it's going to be a fraction of the solution here.
Yeah.
But I guess I have the impression that the conversation about solutions is a little bit too focused on trees and growing things. just because I don't think there's enough capacity there to really do the job. And I think the real problem is we got to stop burning so much fossil fuel in the first place.
Sure.
And once we've done that, we can think that the trees might help us in the little increment that we didn't solve in the first place. But we have to clean up most of the mess before we can use these second order or other tools. That's my feeling. So it's positive and it's great people are doing it, but we have a big problem, which is fossil fuels.
Okay, thank you. Thank you for doing this.
Joe,
Cynthia, you had a question, didn't you?
all right, Cynthia.
You're muted, Cynthia.
All right. I would like Dr. Keeling to address a little bit more the lag between CO2 rise and then resultant temperature increase. And I know I would be oversimplifying, but is there some sort of a thumbnail factor that we could apply? Anyway, more information about that lag, if you wouldn't mind.
Well, yeah, the point I was trying to make is that there is a way to think about it where there's no lag at all. And that way is that the tons of CO2 you emit cause an increment of warming promptly and permanently.
And what we have already
And the reason that is an okay way of looking at it is it's both a lead. We're front loading the CO2 buildup is kind of front loaded because it goes up and comes down, but the warming that's responding to the CO2 is back loaded because there's a lag for the warming to occur, and the front loading of the CO2 and the back loading of the temperature kind of cancel out.
Well, if we were to stop burning fossil fuels today, how much longer would we expect the temperature to rise?
Oh, if we stopped burning, but by the logic I just get, and it's approximate, but I think it's a good starting point. If we stopped burning fossil fuel today and the land use, we cut that down. And by the way, this is ignoring the other greenhouse gases, of course. But let's suppose we only had a carbon dioxide problem. The other greenhouse gases were minor. If we stopped burning fossil fuel today, we went to net zero today, what would happen is the global temperature would stop warming, but it wouldn't cool.
It would
just
stop
stop
warming
warming.
today.
Yeah.
All right, that's okay. Thank you.
All right, Joe, what's your question?
My question is, I guess several years ago, Dr. Keeling and Ralph Gurney and others did presentation for NCCCA in which they talked about some tools that they've all worked on to help us measure the amount of CO2 in the atmosphere. And as time passes, and as we start implementing climate action plans and so forth, it's important to be able to measure where we are and what progress we're making or not. Those tools have morphed into City Climate Intelligence, which is sponsored by RMI and Dr. Gurney at Northern Arizona University and a whole bunch of others. And so my question is, how do we get those tools into San Diego so we can evaluate progress that we're making or not with respect to removing emissions or removing the harmful CO2, et cetera?
Yeah, and Joe asked me this question in the lead up when people were joining. It was kind of informal, and so far this tool, that to my knowledge, has been applied in a research context, and so it's been supported through funding for projects that are on cities that are being used as test beds for various federal funded programs or other funded programs. And so the fast way to get San Diego in that would be to bring it into one of these programs. And I actually am interested in the combined, there's this is another important sort of part of the research portfolio now, and it is that I mean, let's talk about, what we experienced with COVID. I mean, so people stopped driving cars and the air quality got better. So it's pretty clear that there's strong synergies between the measures that a city takes to reduce its CO2 emissions and the measures it takes to clean up its air quality. And so it makes sense to look at the two together in the context of improving the city and its portfolio of emissions. And what Joe is talking about in terms of technology was that there are both ways to using kind of big data, geographic information systems to calculate where we think CO2 emissions are coming from in a city and by how much. And then you can verify that by actually looking at the plumes of carbon dioxide and other gases in the city as you drive around or as you have an instrument here and there. And so you can build the system and you can really validate it. And so you can have a pretty good idea of what's going on around the landscape. And those are good tools for policymakers to figure out what, where should San Diego invest to reduce its emissions? Obviously, if you're going to reduce carbon dioxide emissions, you got to reduce vehicular emissions. You got to clean up power plants, use solar as much as you can, go to electric vehicles. But how important are the landfills? How well do we really know the emissions of methane from landfills? And that's a little harder to do unless you have some kind of verification methods, or how much is coming from wastewater treatment. And maybe there's CO2 emissions from things we don't know about. Maybe we're not actually tracking all the fuel being burned, for example, or maybe maybe just the counting is off. And so there are errors like that, and you'd like to know that. And so there are ways to bring that together, combining people doing measurements like I do in the air with like what Kevin Gurney does, doing the bottom-up accounting, to develop an information system that's powerful both for the policymakers and also for ordinary citizens to look out and see what's actually happening on the landscape. And it can interact not just with, it's relevant not just for tracking greenhouse gas emissions, but also for pollutants that affect air quality. So I do think there's an important step forward that cities should take and San Diego should take like that. And
could you point us, Dr. Keeling, could you point us to who to reach out to get specific about bringing these technologies and tools here?
Yeah. I think the question that you're asking, is there a citizen science way to do this? That's almost what you want. And I don't think we have that yet. We only have a sort of research package way of doing it.
Can we bring the research to San Diego?
Yeah, that's what I was saying before.
How do we do that? I mean, you don't have to answer right now, but we send you an email. Would you be able to respond with some steps or people to contact or whatever?
Yeah, well, really, my reaction is, we're in the federal funding portfolio. Are we going to carve out some money for this? Right? Because I don't think the city of San Diego, the county is not going to pay for this, because it doesn't look like the kind of things that they'll look at it and say, yeah, that's a luxury we can't afford.
Yeah, perhaps. But if we take actions on implementing cap measures and we don't know whether they're having any impact, what value is there? I mean,
exactly. Yeah.
Thank you.
Yeah.
Well, we should probably wind down unless somebody has a burning question. But we should probably respect everybody's time. So we want to thank you so much for joining us tonight, and for all the participants, for everybody also.
Well,
thanks for all your great questions.
Yeah, thanks for the opportunity. I really appreciate it. And thanks.
And we'll really try to.
Yeah, thanks for your efforts.
Yeah, we'll really try to stop burning fossil fuels.
Great.
And to what, Cynthia?
I'm just telling our speaker, Ralph Keeling, that that was great storytelling on your part. You did a nice job of explaining.
All right. thanks.
Yes.
Yes.
So,
And, you know, we just have to, I think we just have to keep our elected officials, make them responsive to us and hold their feet to the fire and elect people that'll do the job. That I don't know what else we can do. We can do all these, plant our gardens and do these individual things, but they're not going to get us anywhere, like you said. It's all industrial.
well,
Right.
yeah, and embrace other ways of moving around. Because we do need to,
Right,
we do need to
exactly.
get out of our cars,
Sandex, 5 big
Yes.
moves.
whether mandated or not. We have to make that fun and efficient.
We're doing that right now in this meeting,
Yeah, yeah, exactly.
right?
Yep.
This is a
Right.
big part
That's
of the
why
solution.
yeah, that's why we have these Zoom meetings to reduce our carbon footprint.
All right.
Okay.
Thank you, guys.
Thank you, everybody.
Thank you.
Bye-bye.
Bye-bye.